P inverse AP is equal to D. So that's what it means for a matrix to be diagonalizable. And last time we realized that if you create P out of eigenvectors of A, so if you create a matrix P, which is V1, V2, Vn, then A times P is equal to P times a diagonal matrix. And that diagonal matrix was the corresponding eigenvalues of these eigenvectors. And this is the important thing to remember, because it lets you realize that A is diagonalizable if and only if you can find n linearly independent eigenvectors of A. And this is actually a theorem. And so the reason if you can find n linearly independent eigenvectors of A, then you can use them to build a square matrix P. Now, you've studied invertibility for your test, and you remember that a matrix being invertible, there were a bunch of equivalent conditions. The matrix is invertible if it has full rank. The matrix is invertible if the only solutions of that matrix times x equals 0 is the 0 solution. The matrix is invertible if its column space is Rn. The matrix is invertible if its row space is Rn. The matrix is invertible if its rows are linearly independent. And the matrix is invertible if its columns are linearly independent. So if I have n linearly independent eigenvectors, and I build a matrix by filling in the columns with those eigenvectors, what can you tell me about that matrix? It's invertible. Because the columns are linearly independent, that tells us P is invertible. And that tells us that AP equals P times the diagonal matrix made out of eigenvalues. So this is a diagonal matrix made out of eigenvalues. I've used the MATLAB notation. Means that we can just left multiply by P inverse. And we're done. So this is actually the proof. This is the proof that if you can find n linearly independent eigenvectors, then A is diagonalizable. Going in the other direction is actually easier and shorter, so I'm not going to present it. So we see that whether or not a matrix is diagonalizable boils down to whether or not we can find a full set of linearly independent eigenvectors. Now, before I proceed with that, let me give one more definition because it's going to be useful in a moment. So, definition. Two square matrices are similar if, okay, so two square matrices A and B are similar if there is an invertible matrix P so that P inverse A times P is equal to B. So this is just a new language. We're going to use it in a moment. So fact, if A is diagonalizable, then A is similar to a diagonal matrix. This is combining, this is just using the definition of diagonalizable and the definition of similar. And this blackboard for the moment seems useless and empty, but we will use it in a moment. Okay, so let's just review what we did before. So at the end of the last class, I had A is the matrix -7, 2, -4, 8, -1, 4, 18, -6, 11. And the question was, is this diagonalizable? And so we have, this is several steps. So step 1, find eigenvalues. And so for that, we computed the determinant of A minus lambda I. And we found that it was equal to minus lambda minus 1, lambda minus 3, lambda plus 1. So the eigenvalues, first eigenvalue would be 1, second eigenvalue would be 3, third eigenvalue would be minus 1. Quick question, is there anything magical about the first eigenvalue being 1, the second eigenvalue being 3? I just happened to read it out of that, but if I had factored it in a different order, I would have the eigenvalues in a different order. So here when I say first, second, third, I'm just listing them. There's nothing special. I didn't use any specific ordering. I just needed to be able to talk about a first eigenvalue, a second eigenvalue, and a third eigenvalue. Step 2, find corresponding eigenvectors. So first I had to solve A minus 1 times the identity times x equals 0. Then I had to solve A minus 3 times the identity times x equals 0. And then I had to solve A minus 1 times the identity times x equals 0. From this, I got an eigenvector. V1 is minus 1, 2, 3. And you can check that this times this is equal to 1 times this. From this, I got an eigenvector V2, which was minus 1, 1, 3. And from this, I got an eigenvector V3, which was minus 1, 1, 2. Each of you could have come down to a different eigenvector, because if you take an eigenvector and multiply it by any non-zero number, you get another eigenvector. So there's nothing special about these eigenvectors except that I find them aesthetically pleasing and that they involve small integers and and they don't have fractions, right? But you can come up with your own eigenvectors as long as they're non-zero and they work. So step 3, build P and D. Now, one student might have P is minus 1, 2, 3, minus 1, 1, 3, minus 1, 1, 2. And for this student to be correct, what must their diagonal matrix be? What's the first entry? 1, 3, minus 1. Now, some other student might come up with P hat, which is minus 1, 1, 3, minus pi, pi, 2 pi, minus 10, 20, 30. In which case their diagonal matrix would be what? Hold on. So this has to be the eigenvalue corresponding to this eigenvector. What is that eigenvalue? 3. This has to be the eigenvalue corresponding to that eigenvector. Minus 1. And this 1. Okay? Now, step 4, check that P is invertible. If P is invertible, it will then follow that P inverse A P is equal to D. Or P hat inverse A P hat is D hat. Students 1 and students 2 will have diagonalized their matrices correctly. So to check that P is invertible, we could compute the determinant. We could check that the columns are linearly independent. To save us, there's actually a theorem which says any set of eigenvectors with distinct eigenvalues is a linearly independent set. And I'll try to prove this theorem by the end of class, but I can't promise I will. Here I have 3 eigenvectors. I want to know, are those 3 eigenvectors linearly independent? I look at their eigenvalues. One eigenvector has eigenvalue 1, one eigenvector has eigenvalue 3, one eigenvector has eigenvalue minus 1. So my 3 columns, are they eigenvectors with distinct eigenvalues? Yes, because 1, 3, and minus 1 are distinct values. There's no stuttering. By that theorem, they are linearly independent. And we're done. So that's this example. Now, I would like you to just quickly notice a few things. So first of all, the eigenvalues of A, well, we computed them. They are 1, 3, and minus 1. The eigenvalues of D So here's D. I want the eigenvalues of D. So that would be the determinant of D minus lambda I. That would be the determinant of 1 minus lambda, 0, 0, 0, 3 minus lambda, 0, 0, 0, minus 1 minus lambda. So please compute that determinant and factor it for me. OK, done? Great. You got lambda minus 1, lambda minus 3, lambda plus 1. So what are the eigenvalues of D? 1, 3, minus 1. In general, if you have an upper triangular, lower triangular, or diagonal matrix, the eigenvalues are on the diagonal. Now, let's compute the trace of A and the trace of D. So the trace of A, what that means is add up the diagonal entry, add up the things on the diagonal. Minus 7, minus 1, plus 11. If I add up the diagonal entries on D, I get 1 plus 3 minus 1. What do these things add up to? 3. If I compute the determinant of A and the determinant of D, the determinant of D, can you do that for me? Minus 3. The determinant of A, given enough time, can you do it for me? You're going to have to do a cofactor expansion. You're going to have to compute 3 2x2 determinants. Are you confident you could compute that determinant for me in 5 minutes? Yeah, so it would be minus 7 times the determinant of minus 1, 4, minus 6, 11, minus 2 times the determinant of 8, 18, 4, 11, minus 4 times the determinant of 8, minus 1, 18, minus 6. Yep. And you would compute those 2x2 determinants, and you would do some calculations. And you know what you'd end up with? Minus 3. This is not a coincidence. This is a theorem. And in fact, there's a further part, which is that the rank of A equals the rank of D. All right. So next example. So the next example, again, is one that we did in class. OK. So A is 3, 1, 1, 1, 3, 1, 1, 1, 3. Is it diagonalizable? So the first step is we computed the determinant of A minus lambda I. And after some pain and suffering, we got to lambda minus 5 times lambda minus 2 squared. This gives us one eigenvalue, which is 5, another eigenvalue, which is 2, and a third eigenvalue, which is 2. And whenever you see this, you should begin to feel this, which is cautious. We have algebraic multiplicity greater than 1. OK. Step 2, find the corresponding eigenvectors. So first we solve A minus 5i times x is 0. And that worked And we got an eigenvector 1, 1, 1. Then, the good news is we only had to do one linear algebra problem because we had a repeated eigenvalue. A minus 2 times the identity. And this led to eigenvectors minus 1, 1, 0, and v3, which was minus 1, 0, 1. And you can check these are actually eigenvectors. You just multiply them by A. Step 3, build P and D. Okay, so I need to use my eigenvectors to build a matrix. So let's go ahead. So there's no particular reason, but we'll just do it in this way. Minus 1, 0, 1. What is this entry? 5, 0, 0, 0, 2, 0, 0, 0, 2. Great. Check that P is invertible. Step 4. Check that P is invertible. So I would like to know that I have 3 linearly independent eigenvectors. Do I have 3 linearly independent eigenvectors? All right, so let's look at them. First of all, I have v2, v3, which came from the general solution of a homogeneous problem. These came from the general solution of a homogeneous problem. Are they linearly independent? Yes, because the 1s and 0s conspire beautifully. And this you know because you've studied hard for your test in an hour and 25 minutes. Right? These are linearly independent. And they have eigenvalue equal to 2. Now I would like to toss in v1. So this has eigenvalue 5. These are linearly independent. Is there some reason why I know that v1 is independent of v2? Because they have different eigenvalues by the theorem. And I know that v1 is independent of v3 because they have different eigenvalues. So this is linearly independent. And therefore my P is invertible, and I'm done. So A is diagonalizable. Now we can quickly check. The eigenvalues of A, we computed them. They are 5, 2, and 2. The eigenvalues of D, they're staring us in the face. D is a diagonal matrix. The trace of A is 3 plus 3 plus 3. The trace of D is 5 plus 2 plus 2. 9, 9. The determinant of A is a mess. The determinant of D is what? 20. This mess does equal 20. And the rank of A equals the rank of D which equals 3. The fact that this is true is a theorem. The fact that this is 20 without actually computing that mess is a theorem. Okay, another example. Okay. -2, 1, 0, 0, -2, 0, 0, 0, 4. All right. So step 1. Is this diagonalizable? It looks so close to being diagonalizable. Maybe we can somehow get rid of that 1. Find the eigenvalues. So I compute the determinant of A minus lambda I. And I'm going to get -2 minus lambda times -2 minus lambda times 4 minus lambda. Because you know how to compute determinants of upper triangular, lower triangular, and diagonal matrices. This is what type? Upper triangular. If I subtract lambda off the diagonal, it is still upper triangular. So my eigenvalues are -2, -2, and 4. Oh, there they were on the diagonal. That's not surprising. Here, these are repeated. They have algebraic multiplicity. How many times are they repeated? 2. And I'm cautious. Find corresponding eigenvectors. So this one I'll actually do slowly. Okay, so A. I want to solve A minus -2 times the identity times x is 0. So that has the augmented matrix. I'm going to subtract -2 off of the diagonal. So subtracting -2 is the same as adding 2. So I get 0, 1, 0, 0, 0, 0, 0, 0, 6. And 0, 0, 0. That's the augmented matrix. So you're in really good shape because you've been studying hard. What's the reduced row echelon form? 0, 1, 0. 0, 0, 1. 0, 0, 0. So the only solution is V1 is any scalar multiple of 1, 0, 0. Because from the first equation, you get that the second component of V1 must be 0. From the second equation, you get that the third component of V1 must be 0. The first component of V1 can be anything at once. B was solve A minus 4 times the identity times x equals 0. So I subtract 4 off the diagonal, and I get -6, 1, 0, 0, 0, -6, 0, 0, and 0, 0, 0, 4. Okay, again, you're in good shape. You've been studying hard. You're well rested. You've eaten, by definition. Oops. Okay, what is the reduced row echelon form? Okay, so can you set this to 1? Yeah, you're going to divide by 1/6. Can you set this to 1? Yeah, you're going to multiply by minus 1/6, or you're going to divide by minus 6. Can you set this to 1? Yes. Once you've set this to 1, can you knock that out? Yes. Is anything exciting going to happen over here? No. So after a little bit of work, you got that your reduced row echelon form is this. The general solution will have how many parameters? 1. The general solution will have 1 parameter, and we're going to get an eigenvector. First entry must be 0, second entry must be 0, third entry can be whatever it wants. And you can check that is an eigenvector. Okay. Step 3. Build P and D. So P, D. Okay, so first column we can put 1, 0, 0. And we can put in the corresponding eigenvalue, minus 2. Second column, we can put 0, 0, 1, and we can put the corresponding eigenvalue 4. What can we put in here? It has to be an eigenvector. It has to be linearly independent from this and this. Are there any eigenvectors for minus 2 that are not a multiple of this? No. Are there any eigenvectors for 4 that are not a multiple of this? No. Cannot find a third eigenvector that is linearly independent of the 2 we found. A is not diagonalizable. So the only time things are going to go wrong in terms of trying to diagonalize things is if you have repeated eigenvalues and you cannot find as many eigenvectors as there are as the algebraic multiplicity. Here, the fact that we found only 1 meant that this has geometric multiplicity equals 1. If the geometric multiplicity is less than the algebraic multiplicity, stop, you are not diagonalizable. So, word of experience, to know that I was not diagonalizable, did I actually have to do all of this? No, I should have stopped at the bottom of that blackboard because I was not going to get enough linearly independent eigenvectors. Okay, so let's quickly at least prove this thing about the eigenvalues and the determinants because that proof is beautiful. The proof of the trace is very pretty. The proof that the ranks are equal is beautiful and subtle, but not for class time. Anyone who wants it can come see me. So theorem, if A and B are similar matrices, which we write as A tilde B. Don't worry if you can't remember that. Then, 1, the determinant of A equals the determinant of B. 2, the eigenvalues of A equal the eigenvalues of B. 3, the trace of A equals the trace of B. And 4, the rank of A equals the rank of B. So let's prove this, and then I will wave. I'm not going to prove those, although proving the trace would actually take about 2 minutes. So, and notice, did I require that B is diagonal? Or did I just require that A and B are similar to each other? They're similar to each other. It happens that when a matrix is diagonalizable, it is similar to the diagonal matrix. But I'm not going to be using that A or B are diagonal. All I have is that P inverse AP equals B for some invertible matrix P. So I need to be able, that's the only thing I have, and that implies all 4 of those. So first let's just do the determinant. The determinant of B is equal to the determinant of P inverse AP. And this is because A and B are similar. Does the determinant play nicely with products? Does it play nicely with addition? No. It does play nicely with products. So this is the determinant of P inverse times the determinant of A times the determinant of P, because determinants play nicely with products. Now, this is 1 over the determinant of P times the determinant of A times the determinant of P. So just believe me for a moment. I'm saying that the determinant of P inverse is 1 over the determinant of P. If you accept that, what does this equal? Determinant of A. And I'm done. All I need is that the determinant of P times the determinant, that the determinant of P inverse is equal to 1 over the determinant of P. So here, I know, so let's do this. Okay, so the determinant of P times P inverse is equal to the determinant of what matrix? Identity. What is the determinant of the identity? Louder? 1. Now, on the other hand, determinant plays nicely with product. So that's determinant of P times determinant of P inverse. So I would like to say that this means the determinant of P inverse is 1 over the determinant of P. May I say that? Yes. What did I implicitly use? That the determinant of P is non-zero. Because the determinant of P is non-zero, and this is P is invertible. Okay, so this proves that the determinant of A is equal to the determinant of B. Now I want to prove that the eigenvalues are the same, because it's a beautiful proof. So to find the eigenvalues of B are roots of the characteristic polynomial. I'll put a little b there, which is the determinant of B minus lambda times the identity. Is that true? Yes, that's by definition. Now this is equal to the determinant of P inverse AP minus lambda times the identity. And that's because A and B are similar. That means that B is equal to P inverse AP for some matrix. So now I have to think. I would really love, somehow I would like to end up at determinant of A minus lambda times the identity, which would be the characteristic polynomial for the matrix A. Because if this polynomial is equal to this polynomial, then they have the exact same roots and they have the exact same eigenvalues. So the only question is, how can I get from here to here? I've already seen once that I can do clever things with determinants and products. But that would involve somehow getting this thing factored. And here I've been telling you over and over again, well, maybe not over and over again, but you've learned on some level determinants do not play well with addition or subtraction. So I need to have some smart thing that allows me to maybe factor out a P inverse and factor out a P. Because if I could factor out a P inverse on the left and a P on the right and leave behind A minus lambda I, that would be super cool. P inverse AP minus lambda, P inverse identity P. Is that legitimate? Yes. Is it sort of perverse? It seems a little bit like a strange thing to do, unless you know what you want, which is to somehow get here. This is the determinant of P inverse times the determinant of A minus lambda times the identity times the determinant of P. And so here I just use the fact that P inverse AP minus lambda times P inverse identity P is the same thing as P inverse A minus lambda times the identity P. And then I use the determinant plays well with products. So the eigenvalues of B are roots of this characteristic polynomial, which is the exact same characteristic polynomial you get when you're looking for eigenvalues of A. B and A have the same characteristic polynomials. They have the same eigenvalues. I think this is incredibly cool and beautiful, but that's maybe why I went into math. Are there questions? So let's finish with one last example. So 1 minus 5 minus 3, 0 minus 2, 0, minus 3, 7, 1. Is this diagonalizable? Step 1, find the eigenvalues. So this means I'm going to need to compute the determinant of 1 minus lambda, minus 5 minus 3, 0 minus 2 minus lambda, 0, minus 3, 7, 1 minus lambda. Is this a determinant you can compute without too much pain? It's not as easy as upper triangular, lower triangular, or diagonal. But how would you go about doing this one? You'd expand about what? The second row. So this is going to be minus 2 minus lambda times the determinant of the matrix 1 minus lambda minus 3 minus 3, 1 minus lambda. And when you expand that out, you get minus 2 plus lambda, lambda minus 4, lambda plus 2. Okay, so we have one eigenvalue, which is 4. We have a second eigenvalue, which is minus 2. And we have a third eigenvalue, which is minus 2. So we have algebraic multiplicity 2. And we're careful. We find the corresponding eigenvectors. And what happens is when I look for the eigenvectors for eigenvalue 4, I get v1, which is minus 1, 0, 1. When I look for eigenvalue minus 2, I get v2 is 1, 0, 1. And so this matrix is not diagonalizable. A is not diagonalizable. On the other hand, P inverse AP is equal to 4, 0, 0, 0, minus 2, 1, 0, 0, minus 2. Did I get them in the right order? Okay. You can check this at home. Minus 2, 1, 0, 0, 4, with the matrix P, which is 1, 0, 1, 2, 1, 0, minus 1, 0, 1. And this is the Jordan Canonical Form theorem. It's hugely important. It tells you that every matrix is either diagonalizable or it is similar to a matrix which has eigenvalues on the diagonal and has zeros or ones directly above the diagonal. Every matrix is either similar to a diagonal matrix or it is similar to a matrix which has the eigenvalues on the diagonal and zeros or ones directly above. It's incredibly important. It's not in the course. Google it. It's useful. It will come again next year. So good luck with your exam. Thank you for coming to class.